3, 2, 1. Welcome to our Chapter 11 lecture video. Today we're going to talk about gases and the calculations that surround them. This is mostly going to be a mathematics chapter. We're going to start with some conceptual stuff about the physical properties of gases. We introduced this in the first unit in chapters 1 through 4. After we introduce those physical properties, we're going to talk about the simple, combined, and ideal gas laws. The ideal gas law that you need to most be concerned with is PV equals nRT. You don't have to really memorize any of these. I'll give you a chart from the textbook that gives you all of the combined, simple, and ideal gas laws. At the very end, we'll go through some more applied problems as well as partial pressure. Partial pressure is just the relative percentage of gas that makes up a relative percentage of the entire pressure. Whatever the percentage of gas you have, that's the percentage of the total pressure it makes up. Pretty simple, but we will go over a couple calculations with this as well. Kinetic molecular theory is our model for how we define what an ideal gas is. So we have non-ideal gases and ideal gases. Ideal gases are ones that behave like we would like them to and don't have any complicated calculations with them. So an ideal gas assumes that we have motion, constant motion of the particles, as well as no attraction between these particles. If they collide or bounce into each other and don't react with each other, there's no transfer of energy. They don't interact other than they perfectly or elastically rebound off of each other. Gases have incredibly low densities. This is because there's an enormous amount of space between the molecules. They have so much energy relative to their intermolecular forces that they're able to space out to a huge degree. This is why gases are compressible. And the final thing is that temperature is directly related to the internal energy and the speed. Internal energy and speed is essentially synonymous for a gas particle. As temperature increases, so too do those variables as well. So, basically what we just said, but in word format instead of just a little picture and me talking over it. So you can pause this, review it. Like we said, or I said, gases are compressible. This is because the large amount of space between them. We can use this to store gases at various pressures. So if you've ever seen a high pressure cylinder, that's some amount of gas that would be hard to use at atmospheric pressure. So we pressurize it into a vessel where you can distribute some amount of gas with high concentration compared to what we have in the atmosphere. Liquids and solids, they don't have this space in between their molecules, so you can't compress them. Whatever the volume of a liquid and solid is defined. The volume of a gas is not defined until you pressurize it to extreme levels and go beyond the ideal behavior. If you go to extreme pressures, you don't have an ideal gas, you have a non-ideal gas, and then things get a little bit more complicated. The last physical property of gases that we're going to talk about is that gases don't have a defined volume. They'll fill the volume of their container. So just a reminder to our first unit, solids have a definite shape and definite volume. Liquids have an indefinite shape but definite volume. Gases have an indefinite shape and indefinite volume. So they'll form to their container and they'll form to the pressure of the situation that they're in. We can't really pressurize anything other than a container, so kind of a good way to think of it. The book uses this example to show how much of a difference there is in the density of liquid water and gaseous water. So it's almost 1,000 times, 2,000 times difference in the volume. So the density of regular water at room temperature is about 1 gram per centimeter cubed. At its boiling point after it's vaporized, we have 0.0006 grams per centimeter cubed. Very large difference. Gases are very, very disparate in their spacing. Pressure is something we're going to deal with. PV equals nRT. P means pressure, V is volume, N is the number of moles, R is a constant called the ideal gas law, or ideal gas constant, named after the ideal gas law that we'll introduce later, and T is temperature. Pressure is just the result of all the microscopic collisions of the molecules. So if we take all the force of those collisions, sum them up over some given area over a unit time, the unit time is usually per second, but however physicists decide to do it is really up to them. We don't really do these type of calculations, but Pressure is a quantity that we can measure in the lab and we will use for these ideal gas calculations. They result from all the microscopic collisions that bombard us on, the nanosecond scale, as well as the nanometer scale. So pressure, if you have a whole bunch of particles in there, they're going to be colliding. They're going to be interacting a lot more than if they were at a lower pressure or if there were less particles per unit area. Because of these extra collisions, there's going to be more force per unit time. More force over the given area is going to lead to a higher pressure. So the base unit for pressure is Pascal. We will almost never use this other to convert out of it. The ATM is what we're most comfortable with. This is the pressure of Earth at sea level. It doesn't really change much from sea level to the mountaintops, but 1 ATM is this many pascals. Millimeters of mercury is the most common laboratory measurement because mercury is very dense, and we can use a vacuum tube like this type of setup to aspirate mercury. We can figure out how much volume we've aspirated based on the density and the volume of mercury displaced. So this is a very common lab measurement. Millimeters of mercury is the same as torr, which is named after an Italian scientist. That's probably the reason why most physics is done in torr instead of millimeters of mercury. Chemistry, we like to measure things with mercury. More and more that becomes not popular since we're aware of the toxicity of mercury, but you absolutely still see it in analytical labs as well as many research institutes. Our other units are PSI. I've never seen inches of mercury, to be honest, but it may exist in some American labs. Here's going to be the unit conversion table that I'll provide on the exam. So table 11.1, be familiar with it. All of these are in reference to an ATM, 1 atmosphere. So, 101,325 pascals or 100.3 kilopascals equals an atmosphere. Likewise, all these other numbers equal 1 ATM in terms of the given unit. So we could do unit conversion type calculations, just like we did in chapter 2. We have our conversion from the previous chart. 700 millimeters of mercury is equal to 1 ATM. We want to arrange that so that ATM cancels out, and we get the desired unit at the end of the day, millimeters of mercury. So if you were trying to target a certain pressure for a reaction in a laboratory setting, you might have to go from the published ATM to the practical millimeters of mercury. Typically, we go from millimeters of mercury to ATM, but we can do it either way. So our first ideal gas law, or simple gas law, because we typically only refer to them as the ideal gas law for PV equals nRT. The simple ideal gas laws usually get abbreviated as the simple gas laws. Boyle's law will be the first one we talk about. He was a scientist that looked at the difference between pressure and volume. He found out that there was a inverse relationship between these. As one increases, the other has to decrease. The mathematical relationship for that is that we multiply them together. Boyle's law can be used to explain a bicycle pump. There's a one-way valve. We increase the pressure. That decreases the volume. The volume wants to escape somewhere, so it escapes into the tire until the pressure delivered by the pump is not greater than the tire. Through Boyle's experiments, he was able to figure out the proportionality between volume and pressure. And so this little alpha sign down here means proportionality or proportional to. And so how we typically use this equation is P1, or the initial pressure times the initial volume, is always equal to some constant. This first half of this relationship is the definition of indirect variation. When we talk about some of the other variables, we'll see the definition of direct variation. Direct variation, they divide each other. Indirect variation, they multiply each other. An indirect variation, like we have with pressure and volume, as one goes up, the other one has to go down to maintain some constant value. So if we set the initial pressure and initial volume equal to the secondary pressure or final pressure and final volume, you'll be able to solve for whatever value you're missing. The way Boyle actually discovered this was by taking a J tube of mercury, capping it, filling it with more mercury, seeing the displacement of the volume or the difference in the volume, and seeing that that was in change to some pressure, some force, the weight of the mercury that he poured in over the area that it was distributed, or the volume of the graduated flask that he had there. So we get this type of curve when we have indirect variation. When we have direct variation, we have a straight line curve. Indirect variation, we have this kind of L-shaped curve. So here would just be a representation on the molecular scale. If we increase the force pressing down, or the pressure, the force over some area, the area would be this plate, or any other surface that you wanted to consider. As we increase the pressure, the volume will decrease. This causes more and more particles to collide, which cancels out the weight that's pushing down on the vessel that we have here. So these are the type of questions that you can expect to see. All of the simple gas laws are just plug and chug type questions. You'll be given 3 or more variables. You'll have one missing variable. In the simple gas laws, you'll always be given 3 variables. You'll solve for the missing variable. You'll have to rearrange or isolate for that missing variable. So we have P1 times V1 equals P2 times V2. We just need to divide by P2, and then we get V2 all by itself. This could be a solution map that you could come up with. We could then plug everything in given the values and find out that the second volume given this pressure change is equal to 24 liters. You want to do some logical checks. Make sure that you have correct units. If you're increasing the pressure and you know that these things vary indirectly, you can see that from the equation. As one goes up, the other needs to go down for them to maintain a constant value. You should realize that given these type of circumstances, the volume should increase. Other type of circumstances, you should be able to predict the general outcome, even though you wouldn't be able to predict the numerical outcome. Here'd be another example of this problem where we're giving, milliliters and atmosphere. We're missing our second pressure, so we want to rearrange for P2. We could do that by dividing by V2 and plugging in all of our values. Make sure that the units make sense. The book really likes scuba diving, so this chapter does a lot of snorkeling, free diving, scuba diving. That just must be their hobby. The next simple gas law that we're going to talk about is Charles' law. He was another physicist that basically did a bunch of observation on physical state. His observation was one that had a directly proportional relationship. V and T vary at the same. So as V increases, so too does T, or volume and temperature. And so this gives us a straight line graph, but we'll have an equation similar to this. I said that, directly varying relationships are divided by each other. So we can take V1 divided by T1 and set that equal to V2 divided by T2. If you were solving for temperature, you could just start with the equation T1 over V1 equals T2 over V2. We can invert or reciprocate these functions, and it's still perfectly valid. The book mandates that you do everything in Kelvin, but technically for the simple gas laws, you don't have to do it in kelvins. Just like you didn't have to do Q equals MC delta T in Kelvin. You could have gotten away with Celsius. However, it's good to be careful and always convert things into Kelvin, because for the ideal gas law, PV equals nRT, we're going to have to convert everything into Kelvin. So I mentioned that we get a straight line graph. Whether we have a negative or positive direct relationship depends whether we have a positive line or a negative line. In this case, we have a positively correlated direct correlation. So we can use this type of graph to extrapolate what absolute zero is. So absolute zero is something that we've never actually achieved. We've gotten very close, especially in modern technology, but in the era of Charles, they were nowhere even close to getting, even 100 degrees was maybe as close as they were getting to absolute zero. We're within, a couple nano Kelvin from absolute zero, so we very much pushed to that boundary, but there are theoretical reasons for why you can never actually reach absolute zero. At absolute zero, there's no energy in the system. You can't have zero energy in the system. That breaks all quantum mechanical models. And so absolute zero is just a theory that we came up with by extrapolating these Charles law graphs. Absolute zero is very important. We need to have a start point for the temperature. That's why Kelvin is the absolute temperature scale. So if you were to change the temperature of a sealed gas by either immersing it in an ice bath or in a hot bath, you could see that the amount of particles can't change. It's a sealed vessel. Nothing's coming in or out. But the energy of those particles will increase or decrease. As a result, dissolve, the amount of collisions that occur per unit second will increase or decrease. Increase if we increase the temperature, decrease if we decrease the temperature. And the total volume that's displaced by those collisions on average will be so much smaller because there's less energy because of this relationship. So, more plug and chug problems. We have liters initial, temperature initial, liters final. We need to find for temperature final. The book's going to tell you to convert to Kelvin. We could get away without Kelvin because temperature is all going to cancel out, but it's still a good practice. Here's our variables. We can isolate for T1 and then plug and chug. This would be the isolation of T1. Then after we convert from Celsius to Kelvin, which the book will do here for us, we can then plug in our Celsius value for T1 and solve for the rest of the equation. The combined gas law is just the combination of multiple gas laws. This is the most common combined gas law, but you can combine any number of the gas laws. We'll have a table of, I believe it's all 5 gas laws that relate to all 2 of the variables from PV equals nRT. So there's 5 different variations that we can mix those. If we have the pressure and the temperature and the volume, we can plug all of these in to figure out what our missing variable is. In this case, the relationships hold as they did before. Pressure and temperature are going to be directly related. As pressure increases, so too does, or as temperature increases, so too does pressure. As pressure decreases, temperature decreases. This is why when you release a compressed gas, it's very cold. The pressure is reducing, so too is the temperature. Temperature and volume we already talked about, and volume and pressure we already talked about. So we can plug these in to PV over T equals your final PV over T. In this case, we don't have our final pressure, so we'll isolate everything, multiply by T2, divide by V2 to get P just isolated by itself. This is how that would look after we converted to Kelvin right here. In this case, we have the initial and the final temperature, so you should convert both units. Avogadro's law is going to be the last simple law that we talk about. There's also Guy-Lussac's law, but that one doesn't really get much usage. So moles and volume also have a direct relationship. So when we have a direct relationship, we have this linear type graph that we can draw. As the number of moles increases, so too does the volume. As you increase the amount of matter, so too should the volume that matter takes up. This should make sense logically. If I add more stuff, it takes up more space. So we discovered this. Avogadro was very focused on the law. Volume is one of the easiest quantities to observe and measure in the lab. And so you'll notice that all of the laws that we've talked about have volume in them because it's very easy to measure. We can use this direct relationship just like we did with volume and temperature, putting one over the other, setting it equal from the initial to the final conditions. We can give you 3 of these values and you solve for the other one. It's just a plug and chug type problem. If I had a sample of helium and knew the amount of it was, and then I had another sample of helium that took up a different amount of volume, I could figure out how many moles was taken up in the second sample because they're going to take up the same amount of volume per unit element or per moles. So in this case, we would rearrange for N2, multiplying by N2 and dividing by the other variables and multiplying by the other variables that we need. You could invert this equation. That might make it a little bit easier. That's probably what I would do, is invert this equation so that N2 is over V2, and then you can just multiply by V2 and make your life easy instead of cross-multiplying and doing stuff like that. So, just saying some more stuff. Here's what it would look like if we were to plug these values in. Now, like I just pointed out, all of these equations that we've gone over have volume. This is for experimental convenience. If we combine all of these equations together, we get the ideal gas law with the exception of the R constant. R is the ideal gas constant. This can be more generally called a proportionality constant. A proportionality constant is something in mathematics that allows you to convert between a whole variety of units. So you'll notice here that we have volume, moles, temperature, and pressure. R is going to have all of those units so that they cancel out respectively. R is liters times atmospheres per mole per Kelvin. This is going to be the unit of the ideal gas constant for this class. You can switch it to whatever you want. If you want to switch it to liters, bar, atoms, Fahrenheit, you can. That would be really awkward and not very conducive to communicating science, but you could absolutely communicate it however you want. This is how you're going to have to communicate gas calculations. So be familiar with liters, atmospheres, moles, and Kelvin. We already mentioned what all these variables are, but there they are down below. We can do ideal gas calculations based on chemical reactions. So if we have just some change of initial conditions to final conditions, you're going to use one of the simple gas laws. If you have an actual situation presented in front of you, calculate the volume occupied by this much nitrogen at that pressure and that temperature. That's going to be a PV equals nRT. If you see a chemical reaction, you can guarantee that it's going to be a PV equals nRT reaction or equation that you're going to have to use. So in this case, we have moles, we have pressure, we have temperature. We're always going to have the ideal gas constant. So we just need to find volume. We'll just divide the PV equals nRT equation by P and rearrange for V. If we plug in all our variables, this is what we'll get, and we'll figure out that this sample occupies 16 liters at this temperature. Make sure that everything makes sense. We're going to go over what's called standard temperature and pressure, but STP is a very common reference point. 1 mole of gas at 0 degrees Celsius, or this amount of Kelvin, is equal to 22.4 liters. There's also STAP, standard temperature and ambient, or standard ambient temperature and pressure. That one is a little bit more useful because we don't typically do chemistry or live our lives at 0 degrees Celsius, definitely not in California. 25 degrees Celsius is much closer to room temperature, 60, 70 degrees. So SATP gets a little bit more usage, but STP is still a good reference point to kind of think if everything makes sense. If you increase the temperature, well, the volume and pressure should increase too. If you decrease the moles, everything else should decrease as a result. We can just make sure that everything makes sense. It's a good thing to do on the regular. Another example of this problem that requires a little bit more thought is figuring out what the molar mass is. Molar mass is grams per mole. We can solve for moles using this equation. If we're given the amount of grams, we're not going to use grams in calculating anything using PV equals nRT. There is no mass variable in the ideal gas law. So we're going to save the mass term until we're plugging in our moles for the molar mass. The amount of mass divided by the moles that we'll calculate using PV equals nRT is equal to the molar mass. So a little bit more thought than just plugging and chugging. But this is what we would see after we rearrange for moles. We could solve for how many moles we have. This number of moles, pretty small amount. But we also have a small amount of mass, so we could calculate what the molar mass is, 28 grams per mole. If we wanted to, we could then try to derive what the chemical formula was and things like that. But that's not this class. You can do that in an unknown analysis class. Here's going to be the table of all the ideal and simple gas laws that you're going to have access to on the exam. So Guy-Lussac's law is the one that we didn't go over. It's a little harder to measure because it's just pressure and temperature. Measuring volume is a lot easier, and so most of the laws that we talked about involve volume, or all of the laws that we talked about involve volume. So we do have non-ideal gases. The only time we have non-ideal gases is at extremely high pressures where we force these molecules together so much so that they're actually able to interact with each other, and at extremely low temperatures. At extremely low temperatures, these things are moving so slow that they have time to actually slow down as they come into contact with each other, rather than ideal gases where, they're just happy to blaze on by each other. If they smack into each other, they'll bounce, completely elastically off of each other. They're happy to have a lot of space in between them, so they don't have to interact. So We're only ever going to deal with ideal gases as someone who went to grad school. I've never even done a non-ideal gas problem. That's more for physics-based people. There is physical chemistry where you do kind of a interface between the two, but that's not what we're doing here. Partial pressures is going to be the last new topic we talk about. So it's a pretty simple idea. Whatever percentage of the total mixture a given gas is, that's the percentage of the total pressure it's going to make up. So this is the relative percentages of gases in our atmosphere, at least to any reasonable percentage. Anything less than carbon dioxide isn't even worth talking about. So we don't even include carbon monoxide, which is around 0.01% or less, depending on where you live. So we could say that nitrogen, 78% of the atmosphere, makes up 78% of an ATM. Our atmospheric pressure is 1 ATM. Nitrogen makes up 0.78% or 0.78 ATMs. Oxygen makes up 21% or 0.21 ATMs. 0.009, remember, percentage is some decimal times by 100%. So we have to divide our percentages by 100 to get back to the decimal form. Then we would just multiply by the total to get the fractional percentage, or the partial pressure in this case. So, like I just said, 78% of the total pressure is exerted by nitrogen because it makes up 78% of the molecules in the atmosphere. What makes up the pressure in the atmosphere is all the collisions. All atoms in the gas phase take up about the same amount of space because there's a lot of space in between them. Because there's so much space in between them, the size of the individual atom is actually negligible. So we treat all particles in the gas phase as having the same volume of the particle. They can take up different samples of gases, can take up different volumes, but individual atoms only take up an average amount of space based off the pressure. So we could use this, problem right here to say that, 80% is helium, 20% is neon. If we only have one total ATM, we can multiply these relative percentages by the total to get the partial or fractional percentages, the partial pressures of these gases. So Dalton was a physicist who kind of came up with this law and basically, came up with the relatively intuitive idea that if I have a composition of gases that are all combined, the pressures of each individual gas or the amount of each individual gas is going to sum up to make up the total amount of pressure or the total amount of stuff. Back then, very revolutionary. Now, we stand on the shoulders of the people before us, so to speak. Here would be an example of this type of problem. We have 3 gases, or we have a total and 2 other gases. We want to figure out what the pressure of that missing gas is. We can subtract out the 2 given gases from the total pressure to figure out what our final pressure is. In this case, it would just be 150 millimeters of mercury. Again, this is our common laboratory measurement, so this is one that I would definitely be comfortable with converting to and from. Another example is bubbling gas through a liquid so that we can collect the gases over that liquid. This is a old school experiment that is in every single textbook, so don't be surprised if you see problems like this in the homework. They tell us what the total pressure is. We could then look up, or it's given to us, what the pressure of the solvent is. The solvent in this case is water. It's whatever we're collecting over. It's going to have some pressure that we have to subtract out from the total pressure. Whatever's residual is the pressure of the gas in concern. So you could go to some type of table like this. I will always give you tabulated values if you need them. Kind of like I don't make you memorize electronegativities. I'll give them to you if you have to be answered, or if you have to answer a question on them. So what we're going to do is gases and chemical reactions. So this is going to be your challenge question. We'll figure out, the partial pressure of oxygen when we combust something. So related to the challenge question in chapter 8 and 7. So if we had some initial conditions, some amount of volume, some temperature, and some pressure, we could solve for the amount of material being made. If we were given the material and missing one of these other variables, we could solve for it. So if I asked you to solve for the partial pressure, you'd be solving for the pressure of however many moles of a given compound. In this case, we're taking 2 gases, combining them to make a third gas or a new gas. And so the partial pressure of the resulting reaction is the total pressure. So, but in the combustion of octane, you will have multiple products, so you'll actually have to take the partial pressure instead of the total pressure. This is what the dimensional analysis would look like after we convert from moles of hydrogen to moles of ammonia. So it's always good to have some type of check to make sure that your answer makes sense. STP, standard temperature and pressure, is a very good, set point to use. If you have slightly different conditions, you can kind of modulate your expectations based on that. But, in regular chemistry, we're usually pretty close to STP, and we can extrapolate, the temperature value by a little bit. But you're never going to be too much pressure difference if you're doing normal everyday things. So here's just to represent that the same amount of molecules take up the same volume, but the masses can be totally different. We mentioned this before, but the volume of the actual atom is more dependent on the pressure than it is the actual atomic size. When you get to non-ideal gases, atomic size actually matters. But in ideal gases, atomic size is irrelevant. Xenon is orders of magnitude larger than helium, but they take up the same volume at STP. We went over a lot of things. A lot of things are kind of tangential to our main focus. Kinetic molecular theory is just so we can frame the ideal gas law. Pressure was a new unit that we can convert to and from, and we will use in the ideal gas law. The simple gas laws are all of the two variable laws, pressure and temperature, volume and temperature. The combined gas laws are any two combined simple gas laws. If we combine all of the gas laws, we get the ideal gas law. This is our PV equals nRT. This is the most useful equation we have. We talked about partial pressures in Dalton's law, how we could just sum up all the partial pressures to get a total pressure. The partial pressure is the fractional percent of that gas in the total mixture. And then we can do reactions with gases and use PV equals nRT to solve for individual variables. Most important is the ideal gas law, PV equals nRT, but the physical properties of gases and the partial pressure calculations are important as well. If you have any questions on any of this material, make sure to reach out to me in email or office hours. Otherwise, I'll see you in lab next week.